Good day, students. The topic we are considering today is an experiment to determine the specific capacity of a solid by method of mixture. Now, we start with describing it using diagram and experiments. Now, what we need to do, we have to know that there is a beaker. There's a beaker. And we have the Bunsen burner, to apply the heat, and there's water. Inside the water we have the thermometer. We have the thermometer to take the measurement of the temperature. We have the stirrer. We have the copper ball. This is a thread. Right? This is the copper ball or copper metal. We have the stirrer. We have the uniform distribution of the heat, and after that we have the calorimeter, lagged calorimeter. We have lagged calorimeter. In the lagged calorimeter we have the stirrer. We have the thermometer. Likewise, thermometer. We have the stirrer. We have the lagging material. Wood, especially. The purpose of the lagging material is to prevent the heat loss to the surrounding. We have the water here. Here also we have water. And we have the lid to cover the uppermost parts of the calorimeter to prevent heat loss to the surrounding. This mass will be transferred. Let's assume this is our mass to the copper ball. When it's being transferred, this is the lid. The initial temperature of this water before the copper ball is transferred, let's call it θ1. When the temperature is being heated, by the time temperature of the water is being heated or increased, when the copper ball is transferred to it, let's call it θ2. The temperature of the heated copper ball, let's call it θ3. That means that heat loss by this copper ball, because in the course of transferring it, heat will be lost from here to the calorimeter, equals to heat gain. This copper ball, it get lost from this copper ball when you are transferring it. If formally is 100 degrees centigrade, before you transfer it to this place, there will be heat loss to the surrounding. It's lost by this copper ball. And the part of the precaution you have to take is that when you are doing this experiment, is to transfer the copper ball very fast. Another precaution that we lag it around, lag the calorimeter, that the calorimeter is lagged to prevent heat loss to the surrounding. And also the water must be stirred uniformly. In the course of carrying out the experiment, you must be stirring it so that there is uniform transmission of the heat around the water. And the next thing is to write the experiments equation, and you have to know that heat lost, first thing to write, heat lost by the copper ball equals to heat gained by calorimeter plus heat gained by water. As the copper ball is losing the heat, when it comes to this place, the initial temperature of the water is theta1. When it comes, it gains the heat to increase to theta2. Means that when we are doing the temperature difference for heat loss by copper ball, it will be theta3 minus theta2. But when you are doing it for the calorimeter and water, because water and calorimeter they are together, they will have the same temperature, which is theta2 minus theta1. Now you have to follow this heat energy, point of heat energy, MC change in theta, and H equals MC theta2 minus theta1. That's difference in temperature. That's what this change in theta means. Now we apply it here, but when you get to this point, you'll be changing it based on the value you have on your temperature. Now use for copper, but let's say MC for copper, C specific capacity of copper ball. Now let's come to temperature change. You come here theta3 minus theta2, because the relationship between this temperature is between theta3 minus theta2 when the heat is got lost. Now it will now be theta3 minus theta2. Close the bracket. Let's go to heat gain by the calorimeter. Let's use MCA to be different from C for calorimeter. CCA, open bracket. Now have theta2 minus theta1. Because it increased from theta1 to theta2. Theta2 minus theta1, close the bracket, plus. Let's come to heat gain by water. They are in the same, they are together. That's M water, basic capacity of water, the same temperature change, theta2 minus theta1. This is the analysis, how to solve a problem. You don't need to cram any formula, just know what the experiment is all about. Now we are going to calculation now. We need to write the parameters so that it will be very easy for us to solve this problem. A piece of copper weighing 400 grams, that's mass of copper, MC, 400 grams, 400 grams. Take note because the specific capacity is given to us in standard, joules per kilogram per kelvin. I didn't need joules per gram. You leave your mass in gram if it's given in gram. But now it's in standard. I have to convert it. 400 divided by 1000. That's 0.4 kilogram. It's heated to 100 degree. That's temperature, initial temperature of the copper ball. Can call it temperature copper, 1 copper. So that you know that is the initial of the copper, which is 100 degrees centigrade. And then quickly transfer to a copper calorimeter of mass. The mass of calorimeter, call it Ca, so that it will be different from copper. Now is 10 grams divided by 1000. That's 0. 100 goes at 0 point. 100 goes 0. That's 1 kilogram. Now, containing 100 grams of liquid as mass of the liquid, because 100 grams divided by 1000 divided by 1000 equals 0. Let's cancel it. 0.1 kilogram. Now says of a known specific capacity, that we don't know specific capacity of the liquid. You know the specific capacity of the liquid at 30 degrees centigrade. That means that in the copper calorimeter, let's call it theta2 of the liquid that is the calorimeter. Let's call it the liquid C, LC, a liquid calorimeter. Now call it SCA, liquid calorimeter, which is 30 degrees centigrade. If the final temperature of the mixture, that call it theta F, is of 50 degrees centigrade, calculate specific heat capacity of the liquid. That is the specific heat capacity of the liquid. They are giving specific heat capacity of the copper, call it C. The copper, call it CC. Specific capacity of the copper is 390 joules per kilogram per Kelvin. Now, right, heat lost by copper, by a piece of copper, equals to heat gain by calorimeter plus heat gain by the liquid. Good. Now, in this case, it's lost by copper. Let's now write it: mass of the copper, specific capacity of the copper, and temperature change, which is theta1 C minus final temperature is called 1000 common, equals mass of the calorimeter, specific capacity of the calorimeter, and we use this one because copper is also used to make the material. Sometimes they will give you one specific capacity for copper, use it for the calorimeter, except otherwise stated. C, and now temperature difference will now be theta F final minus theta 2 LCA. So that's liquid in the calorimeter. Together, that's why I put it here. They have the same initial temperature, plus mass of the liquid, ml, specific capacity of the liquid. That's what we are looking for. They have the same temperature difference, theta F minus theta 2 LCA. Let's start the substitution. The mass of the copper is 0.4 multiplied by specific capacity of the copper 390, theta 1 C 100 minus 50 plus 8 equals mass of the calorimeter 0.01, specific capacity of the copper that was used for the calorimeter. Now it's 390. They are made of the same material. 50 minus 30 plus mass of the liquid 0.1 times Cl. That's what we are looking for. 50 minus 30. Now 0.4 times 390 times 50. When you do a subtraction, equals 0.01 times 390 times 20 plus 0.1 times Cl times 20. Now let's turn it to fraction in the multiplication so that you can really divide. Decimal is 1, fit one number after decimal is 0 times 390 times 50, so 1 over 1. 0 cancel 0. Equals to 1 over decimal is 1, shift 2 times, that's 2 zeros, times 390 times 20 plus 1 over decimal is 1. How many number? L times 20. 0 cancels 0. Now 0 cancels 0. 0 cancels 0. Here, you can say 4 times 5, that's 20 times 390 equals 39 times 2 plus 2C, and so that's 2CL. Now let's multiply 390. When you have 390 like this, bring the 0 at the back up. Yes, multiply by 2. 0, 0 times 0, 0, 2 times 9, 8, carry 1, 7, that's 7,800 equals 39 times 2, 8178, that is 78 plus 2CL. Collect the items, 2CL equals 7,800 minus 78 equals, you press your calculator very well, that's 7722. Now 2CL equals 7722. Divide both sides by 2, that is by 2. 2 cancel 2. Therefore, CL equals 3861 joules per kilogram per Kelvin. This is the end of our class. Please subscribe to my channel so that you can get the latest video. Have a wonderful day.